Good day, students. Welcome to math.serve.com. In this paper, we're going to be going over problem number 10 on our Unit 4 test and application of derivatives. This problem focuses on optimization, and we're going to be looking at a rectangle inscribed in a semicircle. All right? So before we go ahead and solve the problem, let's quickly review the steps involved in solving optimization problems. All right, so here are the order of steps that we are going to follow or should be followed when solving optimization problems. Okay, so number one, you want to model the situation. There are two groups of functions you are going to have. You have the optimization or the primary function, and then you're going to have constraints or the secondary functions. All right, you're going to have a lot of variables all over the place. And in part two, you're going to make a substitution. The goal is to express the optimization function as a function of just one variable as opposed to multiple variables. All right, so you isolate a variable or variables from the constraint and you substitute into the function to be optimized. And then you also want to state your domain constraints on the independent variable. All right. Step 3, that's when we start using the tools of calculus. We're going to find our potential extremas. These are the critical points and endpoints. Part 4, we're going to classify our extrema using the derivative test and evaluating our optimization function at those potential extremas. And then lastly, we'll state the meaning of our result. Okay, so these are the steps that we're going to be following in solving the problem. All right, so if you notice, I have a little guide here of a copy of the document I just went over, so you can refer to it as I solve the problem. So number one, what are we going to do? We're going to model, okay? Now, is it beneficial to draw a diagram in this problem? Absolutely. We want to sketch a rectangle inscribed in a semicircle of radius 5 centimeters. All right, so there goes a sketch of the semicircle and the inscribed rectangle. So the radius of our semicircle is 5 centimeters. Okay, so let's go ahead and generate our primary and secondary functions, okay? All right, so what we're optimizing is what? We are optimizing the area. So what is the area of a rectangle? Let's call this the length right here. So this is the length, and then this is the width, okay? So area is length times width. Okay, so this is our primary function right here. So this is the primary or function to be optimized. Now, what we're doing, we're creating the model, of course. All right, so we need the constraint functions, okay? So we need primary and then secondary or constraint on the dimensions of our rectangle. So let's see, what is our length going to be and what's our width going to be? Now, what is the equation of a semicircle? If you look at this as a coordinate system, we have a semicircle graphed on a coordinate system. Since it's centered on the origin, the equation of the circle, if you remember the formula x minus h squared plus y minus k squared equals r squared, this is the equation of a circle, okay? The standard form of the equation of a circle. So for a circle with radius 5 centimeters, centered at 0, 0, what is the equation going to be? We're going to have x minus 0 squared, which is x squared, plus y minus 0 squared, which is y squared, equals 5 squared, which is 25. Now, if we want to express this as a function of y, we'll have y equals plus or minus the square root of 25 minus x squared. Okay? Just use the procedures of algebra to arrive at this result. Now, since we are looking at the upper semicircle, we'll neglect the negative piece, and the equation is going to be the square root of 25 minus x squared. Now, the beauty of this expression is that it helps us compute or determine the width, because the width is basically the y-coordinate of any point on this semicircle, okay? So the length from here to here is what? This is the x measure, right? So this is x, and then the length is going to be 2x. All right, so the length is 2x. And then what's our width going to be? How wide is this going to be? Well, this is going to be y. Let's rewrite this. Our width is going to be y. Width is equal to y. But what is y? Y is the square root of 25, square root of 25 minus x squared. Okay, so let's put that up here. The square root of 25 minus x squared. Okay, because that's the y-coordinate of any point on this semicircle right here. Okay, all right. So then just put something here just to make it clearer. Any point here, this is x comma y, and it can also be written as x comma what? The square root of 25 minus x squared. Okay, so these two values helps us determine the constraints. All right, so the length is 2x. From here to here is x, so you double that, 2x. And then the width is the y-coordinate, which is the square root of 25 minus x squared. All right, so these two together, this is our secondary or constraint functions, secondary. All right, now we're done with part 1. Now let's shift our attention to part 2. For part 2, that's where we're going to make a substitution, okay? If you look here, we have 1, 2, 3, 4 variables. We just need 2 variables, okay? So we want to express the area as a function of a particular variable. So how about we have the area dependent on just x? Since a is length times width, the length is 2x, and the width is the square root of 25 minus x squared. All right? Now, we also have to state the domain constraints on x for our function here that we generated. So how small can x be? X can be as little as 0. If x is 0, we'll just have a rectangle that's something like this. Let's see, it's just going to be a straight line. This will be our rectangle, kind of like a degenerate rectangle. That will be a rectangle right there. So the lower, x can be as small as 0. Okay, so that's our lower bound. Now, how big can x be? What is the maximum value of x? Well, since the radicand cannot be negative, is going to be undefined, then x squared can only attain a value that causes our radicand to be 0 or greater. Okay, so our upper bound can be determined by solving the equation 25 minus x squared greater than or equal to 0. We have x squared is less than or equal to 25, and then if you read it, if you take the square root, you're going to have the solution to this equation is going to be x is less than or equal to 5. Of course, it's bounded by this piece right here, but we don't need that because we cannot consider anything less than 0, all right? Because we are bounded from below by 0, so we don't look at the other side of our inequality. So this will suffice. So x can be as big as 5. All right. Okay, now with that in mind, let's proceed to part 3, which is the extrema, okay? So for the extrema, we're going to find our potential extremas first before we classify them. So potential extrema. Now, what are our potential extrema? Our potential extrema are our critical points and endpoints, okay? So we have to find our critical points and endpoints. So we're going to do that one by one. Critical points and endpoints. Okay? All right, let's find our critical points first. So critical points, what are the critical points? Critical points are where the derivative is equal to 0 or it does not exist. Okay? All right, so we have our function here, a of x is equal to 2x times the square root of 25 minus x squared. So where is it equal to 0 or non-existent? Its derivative. So first thing we want to do is find the derivative of this function, okay? So let's go ahead and do that. So a prime of x. If you notice, we have two functions here. We have the product of this linear function and then this radical function right here, v. So if you have the product of two functions, how do you find the derivative? You use the product rule, okay? So it's vu prime plus u v prime. Okay, so let's go ahead and apply that here. So we're going to have 2x times the derivative. Well, let's do it the other way. It's going to be v, which is the square root of 25 minus x squared times u prime, which is just simply 2. So we have v u prime plus u, which is 2x times the derivative of v. We're going to be using the chain rule here. So the derivative of the outer function is 1 over 2 root 25 minus x squared times the derivative of the inner function, which is negative 2x. Okay? So we can reduce this. 2 goes here 1, 2 goes here 1. And then we're going to have 2 times the square root of 25 minus x squared plus 2x. Actually, since we have a minus right here, we can change the sign to a negative. Minus the square root of 25 minus x squared. Okay? So we're going to combine these two fractions together so we can easily determine where the function is equal to 0, the derivative function, and where it's undefined. Okay? So how do we combine these two? We just need to find the LCD. The LCD of root 25 minus x squared, and one is root 25 minus x squared. All right, so we'll multiply this denominator and numerator by root 25 minus x squared. All right, so if we carry out the multiplication on the top, you notice that these two radicals have identical radicands. So when you multiply them together, you're going to have 2 root 25 minus x squared minus 2x. And since these two denominators are identical, we can just write them as 1, which is the square root of 25 minus x squared. Okay? So let's go ahead and simplify that. We're going to have square root and square are inverses. They cancel out. We distribute the 2. We have 50 minus 2x squared. 50 minus 2x squared. Yeah, I made a slight error earlier. Let's go up a little bit here. So we have This 2x and then this x, if you multiply them together, this is 2x squared. Sorry about that. So 2x squared. So we have a square here. So 50 minus 2x squared minus 2x squared. And then we divide that by the denominator, which is the square root of 25 minus x squared. Okay, let's simplify that. So a prime of x is simply going to be 50 minus 4x squared divided by the square root of 25 minus x squared. Now let's find where the derivative is equal to 0. Okay, whereas a of x equal to 0, we have to set the entire derivative equal to 0, 50 minus 4x squared divided by the square root of 25 minus x squared equal to 0. If you cross multiply, you have 50 minus 4x squared equals 0. Subtract 50 from both sides. And then if you divide by 4, you have x squared equals 50 over 4, which can be reduced into 25 over 2. If you read both sides, you have x equals plus or minus 5 over root 2. And then this can be rationalized into plus or minus 5 root 2 over 2. Okay, now if you look at our domain constraints, x has to reside between, it has to be 0, between 0 and 5, including 0 and 5. So we have to drop the negative result. Okay, so x is equal to 5 root 2 over 2. And then x is equal to negative 5 root 2 over 2 is excluded. So you exclude that, okay? This is outside the domain, so we're just going to exclude that one. All right, so this is the only critical point that we have. So this is actually, I'm sorry, this is where the derivative is equal to 0. So in order to find the other critical point, we also have to find where the derivative is undefined or where it does not exist. So what causes a rational expression to be undefined? It's when the denominator is equal to 0, right? So we extract the denominator of our derivative, set it equal to 0, square both sides, 25 minus x squared equals 0. You can add 20x squared to both sides and switch the equation around, and then x equals plus or minus 5. Now notice negative 5 is outside the domain, so we cannot take a look at that. So x is equal to 5. X equals negative 5. That one is excluded. All right, this is excluded because it's outside the domain. All right, now we have our critical points, and we know what our endpoints are, right? Our endpoints are the restrictions on our domain. So our critical points and endpoints, critical points and endpoints, also known as the potential extremas, are the following x values: 0, 5 root 2 over 2, and 5. This is the lower bound. This is the critical point that we got, and this happens to be an intersection on an overlap of the upper endpoint and a critical point. All right, so which is a max and which is a min? We do not know. We have to classify them by plugging them into the area function. Okay, so this takes us to step 4, classify. All right, so what is our area function again? Let's go ahead and pull that up. Our area function, a of x is equal to 2x times the square root of 25 minus x squared. So we're going to evaluate the area at these potential extremas. A of 0 is 2 times 0 times the square root of 25 minus 0 square, and you can clearly see that this is 0. A of 5 root 2, 5 root 2 over 2 is going to give us 2 times 5 root 2 over 2 times the square root of 25 minus 5 root 2 over 2 quantity square. All right. If we simplify this, 2 goes here 1, 2 goes here 1, we have 5 root 2. And then in our radical, we have 25 over 1. And then if you square 5, of course, you get 25. If you square root 2, you get 2. And then if you square 2 at the bottom, you get 4. Okay? And then if you simplify that, it goes here 1, it goes here 2. So we have 5 root 2 times the square root of 25. We can just times this by 2 top and bottom to have the same denominator as this fraction here. So it's going to be 50 over 2, okay? So 50 over 2 minus 25 over 2. And then that gives us, let's see what that is. We're going to have 5 root 2, and this is going to be the square root of 25 over 2. We know what the square root of 25 over 2 is, right? Because I think we got that answer earlier somewhere. Yeah, right here. When we took the square root of 25 over 2, it's the same thing as 5 over root 2, okay? This is just going to be 5. So this is going to be 5 root 2 times 5 over root 2, okay? And then you see these two radicals cancel out, and then your answer is going to be 25. All right? Okay, so let's go ahead and find the area of the upper bound, which is 5. So A of 5 is going to be 2 times 5 times the square root of 25 minus minus 5 squared. Okay, so this is going to be 10 times, this is 5 squared, 5 squared is 25, so the square root of 0, so this is just going to be 0 area also. Okay, so we can clearly see that this right here is our maximum. Okay, these are going to be local minimums. This one and that one over there. All right, so all we care about is the maximum. So that's basically the answer. So let's go ahead and contextualize our final result by stating the meaning. Okay, so the largest area is a 5 root 2 over 2 by 5 root 2 rectangle with an area of 25 square units. Okay, so that's basically the answer. Thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to other tutorials such as this. If you have any questions or comments, you can include that in the comment section below. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.